You've probably heard it 100 times. It's not rocket science. Rocket science has been synonymous with extreme complexity ever since the science was created. But complex systems can always be broken down into easily understood chunks if you know where to begin. And today I will begin from the very top. How do rockets work? Thank you for watching, and welcome to the first episode of How Do We Get There? To understand the ultra-complex rockets of today, we need to look at a quick history of how rocketry began. What was the very first rocket? Many historians agree on a machine constructed around 400 BC by the Greek philosopher Archytas, who had built a wooden pigeon suspended by strings that would be pushed around in a circle by a jet of steam escaping from the rear. Ladies and gentlemen, the world's first rocket, a wooden pigeon. But many people associate the creation of rockets with the civilization that invented gunpowder, and not a steamy Greek pigeon. While it is true the Chinese created gunpowder, fireworks, and even rocket-powered arrows using charges similar to today's model rockets, they did so around the 1st century, about 400 years after Archytas' device was created. And please excuse me if I'm mispronouncing his name. I'm an American who is weak in the ways of names that are foreign. The Chinese used rockets for festive occasions as well as military applications for thousands of years, until the British military adopted the technology for their own war efforts in the early 1800s. Rockets were only viewed as possible vehicles after a Russian schoolteacher, Konstantin Tsiolkovsky, again forgive me, when he proposed the idea of using them for space exploration in the early 1900s. He later published a paper detailing how this would be done using liquid propellants, as well as writing the integral rocket equation, the line of math needed to calculate everything a rocket needed to get to a specific destination. He became regarded as the father of modern astronautics for his contributions, and began a path to the stars that is still being built to this day. However, rockets didn't change overnight, as their two main functions continued to be either entertainment or warfare, and the latter drove an explosion of innovation during World War II, with Germany developing the infamous V-2 rocket, the world's first long-range ballistic missile.
You are watching captured German films of the top-secret Nazi research center at Peenemünde, a base on an island in the Baltic Sea. It was here that German scientists developed the first rocket to travel faster than the speed of sound. When it was unleashed on London, it gave no warning of its approach. You heard the explosion before you heard the sound of the missile. The results were devastating.
No longer were rockets dumb canisters of fuel and explosives. Now they could steer, fly vast distances, and eliminate targets with deadly accuracy. If a rocket could destroy a precise target from many miles away, it was no stretch of the imagination to think of a rocket that could fly to a specific point on another world. After the Second World War ended, nations scrambled to get their hands on the brilliant German rocket engineers who had created such terrifying weapons through their research. One of these scientists was named Wernher von Braun, and he had been the one whose research and experimentation had led to the creation of the V-2 rockets. He defected to the United States as the war began to come to a close, and was recruited by the US Army almost immediately, as they knew that the knowledge and capability of von Braun on rocketry was unmatched and would prove extremely useful in their efforts to end the war. Von Braun would later go on to work directly with NASA on satellite launch systems, the Mercury Redstone program, and even the Saturn rocket program that carried Americans to the moon. He became the first director of the then new Marshall Space Flight Center, built by NASA, and held the position until January of 1970, working on many other projects. So rockets began as pigeons, then turned into fireworks and flying explosives for war, then big explosives for war, before being used for the purposes we associate them with today. That's the extremely brief history of the rocket, but now that we know how rockets came to be, how do rockets work in the first place? Modern-day rockets almost universally use liquid propellants, mainly liquid fuel and an oxidizer. The liquid fuel is commonly supercooled hydrogen, but could also be kerosene, alcohol, and hydrazine. The oxidizer is either nitric acid, fluorine, nitrogen tetroxide, and quite simply liquid oxygen. These fuels, while different in composition, achieve the same goal. The oxidizer is mixed with the liquid fuel, then ignited and shot out of an engine nozzle. The liquid fuel is kept separate from the oxidizer to minimize the risk of an explosion, or what is affectionately referred to as rapid unplanned disassembly. Liquid fuel on its own would burn either slowly or inefficiently without the oxidizer, and the purpose of the oxidizer is to provide the burning chemical reaction with oxygen that the flames need to burn the energy being released efficiently. This explosive thrust is channeled down and contained by the engine's nozzle, forcing as much of the explosion downwards into one contained area, though the design of rocket nozzles changes with their environments. For launches on high-gravity planets with thick atmospheres, like Earth, the nozzle will be relatively thin and point all their thrust downwards. In space, there is nothing to push against, so rocket nozzles will be large and will force the thrust into a wide spray. Some engine designs, like the aerospike engine, are perfect for both environments, as the pressure of the atmosphere keeps the spray of the thrust tight. As the air pressure decreases, the nozzle spray will widen, making this engine a valuable single-stage propulsion method. The problem is we haven't really gotten to use one yet, as the heat generated by the engine often melts the center spike, requiring heavy cooling systems that would make the benefits of the engine null due to the extra weight of those systems. So, as a rocket expends its fuel, it is pushed upwards by a perpetual explosion contained within the nozzle, making rocket flight possible. There are a variety of different propulsion methods that we have come up with, such as ion thrusters, which pass a jet of xenon or other ionizable gas through powerful electric fields, ionizing the gas and shooting it out of the thruster at immense speeds. Other futuristic propulsion methods rely on light itself, as miniature ships could extend massive sails to catch laser light shot from a planet or satellite, accelerating the ships to speeds fast enough to be fractions of the speed of light. This makes sense, right? You want the material coming out of or pushing on your ship to be traveling as fast as possible, as that will make your ship go as fast as possible. If liquid fuel can get you up to thousands of meters per second, ion thrusters up to hundreds of thousands, and light itself more than 20% the speed of light, a clear pattern is seen as we trend more and more towards the fastest propellant possible. In my last video, I took this to the theoretical maximum speed with an explanation on how the Alcubierre warp drive would take us to distant places faster than the speed of light. Check it out if you're interested. Okay, so that's how a rocket uses its fuel to fly. But why do rockets break apart multiple times in their mission? Why is this important? Isn't that a waste of a very expensive rocket? Well, picture this. 2 fuel tanks attached to the side of a rocket that has one engine. The left fuel tank will be drained first, then the right. Once the left tank is empty, the right one begins to drain. But now the rocket is carrying around a useless, empty, and heavy fuel tank, making the fuel that is left more inefficient in moving the rocket. If this example rocket ditches the expended tank, it can travel much farther as there is now less rocket for it to move around. This is called staging and is a very important aspect of rocketry. Lower stages of rockets are the first to run out of fuel. Instead of using up the fuel in the upper stages to move the entire rocket around, the bottom stage is detached and other engines more suited to the vacuum of space or the upper atmosphere are deployed to move what is left of the rocket around. In effect, once the lower stage has decoupled, you are left with a smaller, fully fueled rocket that won't have to take its heavy and empty lower reserves to wherever it's going. This saves a ton of fuel, as one single stage rocket would have to be massive to lift the entirety of itself into orbit. But on regular rocket launches, we really don't want an entire rocket in orbit, just whatever it was carrying as cargo, which is much, much smaller and only needs a comparatively tiny amount of fuel to maneuver. However, expending fuel tanks willy-nilly can get expensive, especially if they come down on a town or pollute the ocean with their possibly dangerous materials. Plus, for the next mission you want to launch, you're gonna have to make another one. Many of these empty rocket bodies continue to drift in orbit, which could collide with other more expensive and important satellites as well as stations. This is why SpaceX uses recoverable boosters, as they would not need to make new boosters for the next launch and save the environment from having to break down another lost booster. Also, if you can watch this clip of a rocket coming down from space and landing on a target the size of a couple tennis courts while bringing its speed down to 0 to land on stilts, I'm sorry to say that you do not know the definition of impressive. We've discussed how rockets move around, but what about the things that make rocket science so complicated? Well, to begin with, there's the atmosphere. It's thick and annoying to move through quickly, which is why rockets travel relatively slow through the thickest parts, conserving their chemical energy for when the air will provide the least amount of resistance, and they can finally really begin to accelerate. This is also why rockets are made as aerodynamic as possible, as anything that creates drag will decrease the efficiency of the rocket. But the atmosphere also gives back to us when we need to return, as it can be used as a sort of free fuel. Picture two moons, both the size of our own. One of them is exactly like ours with no atmosphere, and the other one has a thick Earth-like envelope of air. If you wanted to land on the regular moon, you would have to burn fuel to bring yourself to a complete stop and land safely on the ground, requiring large amounts of both rocket and fuel to do so. But with an atmosphere, you can use it to slow yourself down instead of needing fuel to do so. Using a heat shield to protect yourself from the superheated plasma air you create slamming into the atmosphere at tremendous speeds, as well as a parachute to bring your speed down even further for a safe landing, would replace the need for heavy fuel and engines to bring the weight of the craft needing to land down significantly. Another complication in rocket science is powering the ship once it's in space. This is commonly done with solar panels or, for probes traveling far away from the sun that can't get access to as much solar radiation, RTGs, radioisotope thermoelectric generators. These use rods or pellets of radioactive materials that break down within a shielded tube and generate heat. This heat is used to power the spacecraft, and these generators can last ages, but are easy to damage, as a single hole in the shielding would leak precious heat and decrease electricity output significantly. Something else that makes rocket science complex is the crew inside your rockets, as you would hopefully want to keep them alive and sane. This requires pressurized cabins, breathable air, food and water stores, waste management systems, and living quarters for extended missions, as staying in a single cramped capsule for weeks and months will most certainly drive even the most mentally fortified human quite batty. Something else to protect your astronauts against is the radiation that space is absolutely chock full of, especially near a star, like Earth is. And what about your destination? Does it have an atmosphere? How much gravity does it have? Is the surface scorching hot or unfathomably cold? What if it rains molten iron or has winds that travel in the thousands of miles per hour? What if the atmosphere is acidic or crushingly thick? What if you want to land a probe on an asteroid that has so little gravity that if the probe bounced off of its surface, you would never see that asteroid again? What about how you stay in communication with your probe or crew? The farther away from Earth you travel, the longer it will take light or your messages to travel out to the ship, which could prove dangerous if the probe needs to react to a changing condition quickly. This is why distant probes are programmed to act autonomously to situations if connection with Earth is broken. The difficulty of rocket science arises in its complexity. There are a massive number of factors you have to keep in mind when designing a mission. These factors change depending on where you want to go, what you want to bring, and what you want to accomplish. I could spend hours discussing the various incredible designs we have come up with to get to infinity and beyond, but this video is meant to be a quick look at how existing rockets function and act as an introductory lesson in rocket science, as well as something to inspire personal research, as I have most certainly not covered every method of flight or every step in its history. I hope you not only learned something new, even if it was just the existence of a steam-powered pigeon, and maybe inspired you to learn more elsewhere. I hope you had a great day, and shoot for the stars in everything you do. Thank you for watching.